If you've ever tried to build a multi-step AI application, you know the feeling, right? That pain when your pipeline just crashes halfway through. Well, today we're diving into a Python library called dagpipe that's designed to make that whole problem a thing of the past. So let's just start with a pretty stark number. According to recent research, real-world multi-agent AI systems have a failure rate somewhere between 41 and almost 87%. I mean, that's huge. This isn't some tiny little problem. For a lot of developers, it's just the default experience. And the main culprit here is something called cascading failure. Honestly, just think of it like a line of dominoes. One single step fails, maybe a network timeout or a weird response from the language model, and the entire chain just collapses. All that time and money you spent on the previous steps? Yep, wasted. So in this explainer, we're going to walk through dagpipe's toolkit for basically making these failures structurally impossible. We'll kick things off with its core solution, then we'll see how it builds these smart, self-healing pipelines, and finally, we'll look at what all of this actually looks like in practice.
Okay, so how does dagpipe actually solve this? Well, the core idea is elegantly simple. It's all about checkpointing. This slide just nails the difference. On the left, you've got your standard pipeline. It hits an error at step 3, and boom, you're right back at square one. You have to rerun and repay for the first 2 steps. But look at the right. With dagpipe, each successful step gets checkpointed. So when step 3 crashes, you just rerun the script, and it intelligently picks up exactly where it left off.
And the way it's implemented is just beautifully simple. For all your developers out there, there's no complicated database to set up or manage. Dagpipe just writes the output of each successful node to a plain old JSON file. You can literally open it up, look at the data, and you can even manually fix it if you have to. It's just incredibly transparent and so practical. But okay, dagpipe goes way beyond just crash recovery. It also builds some serious intelligence into your pipelines to help manage costs and even anticipate problems before they happen. Now, if you're building anything with LLMs, you know this problem all too well. Why on earth would you pay for a top-tier, super powerful model to do something simple, like just renaming a variable? But in a standard pipeline, you might not have a choice. Dagpipe's answer to this is called the cognitive router. For you, the user, this just means automatic cost savings. But for the developers, the real magic is in the implementation. It doesn't use another expensive LLM call to make these routing decisions. Instead, it uses simple, lightning-fast Python heuristics, like looking for keywords like refactor versus rename, to send tasks to the right-sized model. It's zero overhead for maximum savings. It's brilliant. Okay, but what about problems that are totally out of your control? A free-tier provider could just decide to retire a model without any warning, and your application just silently breaks overnight. This is where dagpipe's self-healing model registry comes in. It's like a proactive shield against these kinds of surprises. When you start it up, it actually checks the provider's API to see what models are available. If the one you want is gone, it warns you and even suggests an alternative before you run a single task. And to keep your startup times nice and snappy, it caches all this data for 24 hours. So we've covered crashes and we've covered infrastructure, but what about just bad data? What happens when a model just gives you garbage? Oh man, it's a constant headache. You ask for clean, perfect JSON, and you get back, you get JSON wrapped in Markdown, or it uses Python-style booleans, or it has all this extra conversational text. And all of that stuff just breaks your parser and fails the whole pipeline. Dagpipe's solution is this really rugged 5-strategy extraction process. It automatically tries to salvage valid data. First, it'll try direct parse. Then it'll strip any markdown. Then it uses regex. Then it'll normalize common errors. And as a total last resort, it'll even try to evaluate the string as a Python literal. It only gives up after all 5 of those strategies fail. But what if a node is just fundamentally broken and it still fails? In most systems, that error context just vanishes into your console logs, lost forever. With dagpipe, it's preserved. And this is just incredible. The failure itself becomes a useful artifact. Dagpipe writes what it calls a dead letter file, and it's basically a complete forensic report. You get the full input data, the exact error message, and the retry count. This makes debugging a total breeze. No more guesswork. So that's all the theory. Now let's actually see what this looks like in practice, right from the command line. So here's the verbose output. On the left, that first run fails at the draft step. Now look at the right.
We just run the exact same command again. And dagpipe instantly skips the completed research and outline steps and picks up right where it left off. You see that? That 7.5 seconds of work from the first run, totally saved.
And you got to understand, this isn't just some optional add-on feature. It is fundamental to how dagpipe is designed. By checkpointing after every single successful step, it makes it structurally impossible for a later failure to corrupt any of your previous work.
So who is this really for? What's the big picture here?
The key takeaway here is that this kind of industrial strength reliability, it's not just for big corporations anymore. Dagpipe is really designed for the individual developer, the student, the tinkerer, anyone who is sensitive to every single wasted API credit and every lost minute of work.
This table really sums up the whole transformation. It's a huge shift from these fragile, all-or-nothing scripts to workflows that are robust, resumable, and cost-efficient right from the start. It's all about making reliability the foundation, not just some afterthought. And that brings us to a final, really powerful question to think about. I mean, if we can finally stop fighting with fragile infrastructure, what new, more ambitious AI applications can we start to build? What does a future that's built on a foundation of reliability actually look like?